Okay, so thanks a lot for giving me this opportunity to talk about my recent paper on super horizon resonant magnetogenesis during inflation. This work I was collaborating with Misa Sasaki and Valerie Vanayat. Okay, so here is the outline of my talk. And so first I'm going to give you the introduction of the project, and then I'm going to give you the super horizon resonant models, which is our models. And then we are going to give you the phenomenological validity of our models and then conclusions. Okay. So introduction. So we have observed the magnetic field on the intergalactic scale, which is around megaparsec scales, and this has been measured to be 10 to the minus 17 to 10 to the minus 14 Gauss, which is around 10 to the minus 23 for omega b, where omega b is the energy density parameter of the magnetic field. Okay, and many people have tried to propose models to explain this tiny number of omega b, and inflation has been a popular working example or working regime to explain these tiny numbers. Okay. So one of the popular models during inflation is this f of phi times f mu nu, where this kind of nominally coupled between the inflaton field and the Maxwell field. And you could have this kind of axial-like coupling models during inflation. And also you can have many models. So the trick to enhance or generate magnetic field during inflation is to break the conformal invariance in the gauge sector. And when you break this symmetry, then you're allowed to enhance the magnetic field to our gauge field during inflation. But in the Maxwell theory, you can imagine that this omega b is very blue tilted, and then after the mode crossing the horizon, omega b decreases exponentially, and then you end up with a small tiny number, okay, even smaller than 10 to the minus 23. Okay, so some obstacles may arise during the production of inflation, because suppose you have some models during inflation, then it might lead to some problem. For example, you have the strong coupling problem, which is due to the fact that suppose you have this kind of model during inflation, and then you have the interaction with the inflaton field and the gauge field. Okay, and once you canonically normalize the gauge field in this manner, essentially you absorb this gauge coupling constant into the gauge field, and then you see that the gauge coupling constant becomes E over F. And typically when you wanted to enhance the gauge field during inflation, you have this guy F squared to be much less than unity, and you see that this gauge coupling constant become much larger than unity, and that breaks the perturbative calculations. Okay. And another problem is the back reaction problem, because you wanted to enhance the gauge field by a lot during inflation, and one might be wondering that once you enhance the gauge field, the omega b, omega e, and other type of matters during inflation might be much larger than unity, and that is going to destroy the background of inflaton. Okay. Anyway, so in the past there was models which consider this kind of type of axial-like coupling f tilde coupled with this f of phi, okay, where phi is the inflaton field. So in this model, you have this kind of equation of motion for the gauge field, and notice that the coupling term here depends on k, on the momentum of the gauge field, okay, and also it depends on the helicity of the gauge field, whether it's plus or minus. Okay, it gets different kind of evolutions. And then you see that once you go to a large scale, to the super Hubble scale, then this coupling goes to 0. So this implies that you only have the sub-horizon amplification of the gauge field. Okay, so you assume that the function, the inflaton field, is a time-dependent function, and then this f of phi just becomes the time-dependent function. And assume that this f is just some oscillating function with amplitude gamma and the frequency omega. Okay, eta is a conformal term, and then you have this kind of equation, which is like the material type equation. And then you know that this material equation has a general solution, which is this e to the mu z, where mu is a Fourier exponent. And this mu is determined by this parameter q, p, and q. Okay. And since you have only the sub-horizon amplification, that means when you go out of the horizon, the mode function freezes. Okay. And then you have just the sub-horizon amplification. So the mode function grows sub-horizon, and then once it crosses the horizon, it freezes. Okay. So now I'm going to show you what happens to omega b in this model. So this is the no-go theorem. Okay. And so what happened is that you wanted to explain this tiny number at the end of inflation, 10 to the minus 23. Okay. So here is the crossing of the horizon, and then here is the end of inflation. Okay. So so like I said, the mode function of the gauge field grows, okay, on the sub-horizon scales, and then it freezes once it crosses the horizon. Okay. So, and then what happens to omega b is that omega b, once the mode crosses the horizon, omega b decreases as according to the expansion of the universe, which is like e to the minus 4 times the e folding numbers. And usually if you put this delta n star to be around 50, which is the e folding number between this crossing until the end of inflation, which is around 50 typically, and then this is going to give you the huge back reaction of the omega b at the crossing, and then this leads to the back reaction problem. This is a no-go theorem. So this means that whatever you do, or whatever mechanism you have on the sub-horizon scales, you are going to face this huge back reaction problem. Okay. So in our model, we propose the following. So we have this kind of coupling between the inflaton field with the Maxwell field. And then also we add the mass term for the gauge field. Okay. And then we consider this kind of background and a time-dependent background for the inflaton field. Okay. And here is the Friedmann equation, and then here is the equation of motion of the inflaton field. Okay. So in this equation, we just neglect the this row of electromagnetic and then the source term here. And okay, so let us study the so the coupling function is just the time-dependent function. Okay. And here we consider it in a Coulomb gauge. Okay. And we can do the Fourier decomposition in this manner. And then equation of motion of this curly A, which is normalized by the square root of f. The big F is defined in this way. And then you have equation of motion for the curly A in this way. So notice that here in this equation, the coupling term here doesn't depend on K. Okay. So that means when you go to the super horizon scales, this term remains. Okay. Unlike the case of the axial-like coupling case, when you go to the super Hubble scale, the coupling term goes away. Okay. And then what happened in our model is the following. So here, this green line represents the previous model, the no-go theorem. And in our model instead, we are going to have the super horizon production. So what happened is that, so the mode grows, okay, the mode, instead of freezing after crossing the horizon, it grows exponentially. So what happens to omega b is that instead of having just the diluting factor here, you also have some growth factor here, mu, which compensates to the expansion of the universe. So what happened here is that instead of omega b goes down as e to the minus 4 times theta n, it is going to be compensated by the growth rate of the mode function. Okay, so this means that there is a chance, there's a possibility of having omega b for the entire period of inflation to be less than unity, and still you can explain this 10 to the minus 23 at the end of inflation. This is the goal. And also you have this 4 constraints coming from this number, back reaction, strong coupling problem, and this theta NCMB large enough. Okay, so in our model we have this kind of behavior of the gauge coupling function, which is positive definite. And in this our setup, we have this kind of equation for the mode function, which is like we take a Hill equation with this time-dependent function here, C, okay, parameters. And in our approximation, one can neglect this term because we are interested in the super Hubble scale where k goes to 0, or you can think of a being exponentially growth function. So you can sort of neglect this term. And then you have this amplitude gamma, and then you have mass term delta. Okay. So we solve that equation numerically. Then here is what we obtained. And this shows the numerical solutions with different value of k, okay? And then the dashed line shows when the mode crosses the horizon. And then you see that once the mode crosses the horizon, it's immediately grows, exponentially grows, okay? With some factor, with some growth factor mu. And then for this, yeah, you see for this red one, once it crosses horizon, it grows almost immediately. And now you see that for different k, it has more or less the same mu, which is the slope of this plot. Okay. And right, so now we have achieved the super horizon amplification of the mode function. And then you can use this kind of approximation with some 4k exponent. And this data set determines the time that the mode function spent outside horizon when it experiences the amplification. Okay, so you can have a blue tilted or skein variant omega b, blue tilted omega b, and red tilted omega b, depending on this exponent mu. Okay, and also you can have the omega m, okay, which is coming from the mass term. Yeah. So we can use the first constraint coming from this omega b has to be at least larger than 10 to the minus 23 to explain the tiny number that we need at late times. Okay. And then we write down this constraint in terms of this x, which is a scale during inflation, x0, kappa, which is the scale of magnetic field, versus CMB scale, and this theta n CMB. So we have this kind of inequality. And the second constraint coming from the fact that we want to avoid the back reaction from omega b, so we have this constraint. Okay, and the next one is to avoid the back reaction coming from omega m, sorry, and we have this another inequality. So, and also the last one is to have the successful inflation, which require on this condition on delta n CMB. Okay. So we combine these three conditions, and then we obtain these three constraints, and then we obtain these three inequalities. Okay, so now we are going to plot these three inequalities in the same plot that shows the scale of inflation and also the spectral index for omega b. So the orange line shows you the black line here show you so you have to be at least 10 to the minus 23, so it has to be above this black line. Okay, and then for the orange line, to avoid the back reaction from omega b, so you have to be below this orange line. Okay, and the last one is to avoid back reaction from omega m, so you have to be below this blue line. Okay, so now you see that the allowed region is this shaded black region. Okay, and then so now you see that NB has to be less than -4. So you are in the sort of red tilted for omega b. And then the scale inflation is around 10 to the minus 32, which is low scale inflation if you want. Yeah. And then the scale of the CMB is around 33. Okay. And now you see that in this plot, the scale invariant and the blue tilted cases are excluded, okay, by all of these constraints. Okay. And now let me just summarize what happened is that this is the green one, the no-go theorem, and here is what we found, okay, the orange line. What we found is that since we have the red tilted spectrum, so our omega b start from the super tiny number during inflation, 10 to the minus 64 more or less, and then it exponentially grows. So that growth factor of the mode function not only compensate the expansion of the universe, but also it wins the expansion of the universe because NB is less than 10, less than minus 4. So you have exponentially increase of the omega b. Okay, so start from tiny number and then you reach 10 to the minus 23. And this delta n star is around 33. Okay. So let me just emphasize that here we have the super horizon production of the gate field that leads to the red tilted spectrum of omega b. Okay. And now let me just say that we also avoid the strong coupling problem by the fact that we can have the hour gauge coupling constant to be much less than unity, and then it evolves to the off order unity at zero inflation. And also we could avoid the back reaction problem from omega e, which is due to the fact that it's because omega e and omega m scales more or less in the same way, okay? And in this manner, 1 over a squared. And once you avoid back reaction of omega m, you automatically avoid the back reaction from omega e, sorry. Right, so conclusions. So we have constructed the model during inflation, and then we have super horizon amplification of the mode function. We obtain the allowed region for our parameters. And future direction is to explore the primordial gaussian wave production in these resonant models. And then we want to study the reheating mechanism. Thank you for your attention.